right, so after talking about Pythagorean with some squares and some square roots, we're actually going to jump to section 4.7 that talks about quadratic functions because there are some squares involved. So we're going to identify graphs of quadratics from tables and equations, and we're going to find the vertex of quadratics. So let's take a peek at quadratic functions. Example 1, find the pattern. All right, I'm looking at this and I see plus 2, plus 2, plus 2, plus 2. Yeah. I see it. So making sure that this is plus 2 for each additional 1 over here, which it is, then I can go ahead and predictively, so an additional 1 over here is an additional 2 over here, an additional 1 in the years is an additional 2 in the price. Got it. Find the pattern. Is this linear or not? Yes. It is linear. Yes, how can we tell? It's a constant change. For each 1 year, there's an addition of 2 in the price. For each additional year, there is a constant change of plus 2 in price. Okay, so constant, I guess I shouldn't have put that in parentheses, constant change of plus 2 in price. Okay, maybe change of should have been in parentheses here, just to show you what I meant grammatically there. And graph this data. Okie 0, 1. First of all, I'm going to label these axes. What is this? Years since 2000. Years since 2000. And price in dollars. Got it. 0, 1, 1, 3, 2, 5 dollars, and 1, 2, 3, 4, and 1, 2, hold on, 1, 2, 3, I'm sorry, 3 and 7. 1, 2, 3, 4, 5, 6, 7. Okay, I see it. Oh. And I have my kid's ruler, so I'm going to use it. Right. There it is. Constant change for each year and linear function. Good. Now let's find the pattern in this. Well, I see plus 1 plus, what's the difference, 3? Plus 5 plus 7, and I'm wondering if you can predict what will be next. Perhaps, I mean, these are odds, perhaps plus 9? Okay, so 17 plus 9 is 26. And then what will we add? Plus 11? 26 plus 11 is 37. And then instead of adding 11, we would add 13. Okay, 47, 50. Yeah? In order to do this pattern. So plus 9, plus 11, plus 13. Now, probably you were thinking, oh, we just keep adding the next odd. And that is a pattern. But what I want you to see is that that means the pattern within, you found a pattern within our pattern. This is like Inception, the movie, right? A dream within a dream here. So plus 2, plus 2, plus 2, plus 2, yeah? Okay, so the constant change actually happened within the pattern. So I like to refer to this, or I learned this from other people, I didn't coin this phrase, as a second layer pattern. So here's our first layer pattern, and then the pattern within our pattern. It's like having a two-tiered problem here, right? Okay, so it wasn't exactly linear, so no. Right? Because the pattern in the price was not for each year. There's an additional plus whatever in price. So for each additional year, there wasn't a constant plus number, right? Plus 2 or plus 1 or plus 3, constant plus whatever in price. That changed. Okay, so it's not linear. Let's graph these points. All right, what do we have here? We still have years since 2000, and we still have price in dollars. Okay, but now we have 0, 1, and we have 1, 2, and we have 2, 5, 1, 2, 3, 4, 5, and then we have 3, 10, 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Somewhere up here about. Okay, so what I'm seeing is that it's bending. So it's not perfectly linear. It's bending upwards. Ah, so this second layer pattern creates curvature in our image. Okay, which brings us to the general form of a quadratic. When we see this second layer pattern, and when we see this bend, then we have a quadratic. Okay, so let's write this down. The general form of a quadratic, which follows the second layer pattern, or is identifiable by a second layer pattern, is y equals ax squared plus bx plus c. Okay, has a second layer pattern. All right, so a general quadratic, so here's the general form of a quadratic, and it has a second layer pattern. Tables and graphs of quadratics. So let's remember these quadratics. Circle which one is a quadratic. Well, this one looks really the same format. Here we know that A is 3, the B is 2, and C is -8. That's a quadratic. It says circle the quadratics. More like an oval or an ellipse, but still. The second one has A equals 2, B, B x's. Well, there are 0 x's, so B equals 0, 0 x's, and C equals 2. But it's still in this format, it's just that there were 0 x's. This is another quadratic. Okay, and now let's look at this one. And we see that, okay, a is 3. What is that? X to the 1.7? No, that does not match this form. The silent exponent on this x is 1. Okay, so if you don't see the exponent, it's a silent 1 here. But this is a problem. Troublemaker. So this is not a quadratic. Okay, if we see a decimal exponent, an exponent higher than 2 on the x's, a square root, I see none of that going on in this situation. So this one does not fit the mold of being a quadratic form. Given that f of x equals negative x squared plus 2x minus 1, compute f of negative 3 and f of 2. Okay, so back to this function notation and just being at ease with it. Okay, so I'm just going to rewrite this a little bit. And remember that f of x is just a name. It's naming y, saying that for every input there is exactly or no more than one output or response, right? So here, this notation doesn't mean f times negative 3. It means x is equal to negative 3 in this scenario. Okay, so if x is equal to negative 3, this is asking what is y when x is negative 3. Let's compute. So f of negative 3 is the opposite of negative 3 squared plus 2 sets of negative 3 and then minus 1. All right, now I need us to be very, very careful. Notice I put in parentheses because this says exponent then multiply by negative 1. So the order of operations says do the exponent first, then take the opposite because that's multiplication. So exponent first, that's 9. This is negative 9. Negative 9 minus 6 minus 1. What is that, negative 16? Okay, so when x equals negative 3, f of negative 3 says y is negative 16. Okay, and now let's do the same thing for f of 2. So this is reading x is taking on the value of 2. Okay, so in that case, f of 2, so when x is 2, the y value, the opposite of 2 squared plus 2 sets of 2 minus 1. Well, exponents first. 2 squared is 4. Take the opposite. That's negative 4. 2 by 2 is 4, so plus 4 and minus 1. Oh, that's 0. Take away 1. It's down 1. So when x is 2, y is negative 1. When x is negative 3, y is negative 16. Got it. Okay, consider y equals x squared. Is this a quadratic function? Okay. So I would say yes. But this is very awkward. This is really y equals 1 x squareds. Even though it's not explicitly written here, this is really saying it's not 2 of them or 5 of them or 8 of them. It's 1 x squareds. 0 x's are showing up here, and plus 0 in it on top of that as a non-x term here. or a non-varying term. So let's see. That means that A is 1, B is 0, C is 0. In order to be in this general form, 1x squared plus 0x's plus 0. So it does work out. I would like to add in if the A is 0, then we're back to having a line. Yeah? So we definitely need A not to be 0. But luckily in this case, it is not. We have an x squared term here. So yes, it is a quadratic. Let's fill in the table of values and graph it. Okay, -3 by -3 is, -3 by -3 is 9. -2 squared, so -2 by -2 is 4. -1 squared, -1 by -1 is 1. 0 by 0 is 0. 1 by 1 is 1. 2 by 2 is 4. 3 by 3 is 9. Got it. Squares, remember, they're that by that. 3 by 3. Literally squares, yes? So just so that, I mean, in my mind, this is, right? Yeah? A literal square, and we are squaring it. A 3 by 3 is 9 in area. A 2 by 2 is 4 in terms of area. Okay, nonetheless, so this was just a just saying, sometimes we have a little bit of a flyaway with our hair. We try to like push it down. Anyway, graph this function. You got it. So I'm going to call this my x-axis and this my y-axis, and I have 0, 0. I have 1, 1. I have 2, 4. 1, 2, 3, 4. And 3, 9 is above. I don't know. It's up here. I have -1, so to the left 1, up 1. X is -2, to the left 2, up 4. 1, 2, 3, 4. Oh, look at that. I'm seeing a smile here. So the graph of this curves. It's got the curvature. Okay, and if you're looking at this, the image of a quadratic is called a parabola. Might as well write that down. Or, I guess I'll wait. Use the graph of this quadratic, so notice it has this curvature, to fill in the table. Okay, so now we have a graph and we're going into the table. I want to just zoom in on the grid here because it's smallish. Okay. I see at -2, so 1, 2. So when x is -2, y is -3. When x is 0, y is 3. When x is 2, y is 5. When x is 4, y is again 3. And then it's saying, when is this again -3? But here, notice it gave us a y value of -3, and it's asking for the x value 6. Got it. And I know it didn't ask for the second layer pattern, but just to kind of look at this, well, these are counting by 2's. -3 plus 6 makes 3. 3 plus 2 is 5. I feel like I would need the in-betweeny values to get this right. Okay. Well, that didn't work out, just because we really are going to need the values between, so -2 and -1, and then 0, and then 0, 1, 2, just to see what's happening here. +6, +2, -2. Interesting. Anyway, okay. Let's find the second layer pattern for this one. And now I'm going to have to sit at home and find all these in-betweeny points and figure that out. It's fine. Second layer pattern for this quadratic. Plot it, graph it. Okay. I do find this amusing that I notice there's normally in our table of values we have a bar separating the two just to organize our thoughts. But let's go ahead and check this pattern out. Let's see, it looks like we subtracted 10, subtracted 6, 9 take away 6 is 3, subtracted 2, 3 take away 2 is 1. Ooh, from 1 to 3 it's an add 2. From 3 to 9, it's an add 6. From 9 to 19, it's an add 10. And now it may not look like there was a pattern here in the second layer, but I swear there is. So from 6 to 10, that is a +4. From 2 to 6, that is a +4. Ooh. Super popular here today. From -2 to +2, that is add 4. -2 plus 4 makes 2. -6 plus 4 makes -2. Okay, so there truly is a second layer pattern here. So there it is. Find the second layer pattern. +4, +4, +4. Plot the points to graph. Okay, I think I'm going to start here at 3, 1. So 1, 2, 3, up 1. 3 to the right, up 1. 2, 3. 2 to the right, up 3. 1, 2, 3. Got it. 4 to the right, up 3. 1, 2, 3, 4. 1, 2, 3. Got it. 1 to the right, up 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. And 5 to the right, up 9. 1, 2, 3, 4, 5. Oh, I'm noticing a certain amount of symmetry. Yeah? For every point, so there's this pivotal point, and then each side has some mirror image point. Okay, so here we go. This one, Y. It's hard for me to connect points sometimes. There. Rough. Should be symmetric, perfectly symmetric. However, I am noticing that this one was x squared, and it's a little bit wider than this one. This one was shifted and moved, so shifted to the right, moved up 1, and it's a little bit narrower. So this pattern, right, a little bit different than just a normal x squared pattern. Let's do it again. Find the second layer pattern for the quadratic, fill in a table, plot, and graph. Okay, pattern. Hunting for a pattern. This is takeaway 7. This is takeaway 5. Okay, in order to get from -7 to -5, that is +2. -7 plus 2 makes -5. So I'm going to have to do this Negative 5 plus 2 is negative 3. So I'm going to use my second layer in order to indicate what should go here in my first layer, actually. Negative 3 plus 2 is negative 1. Negative 1 plus 2 is 1. And do it again. 1 plus 2 is plus 3. Okay, so I'm able to piggyback off of my second layer in order to find the first layer pattern. And then I'm going to use my first layer pattern in order to fill in all of these points. All right, so let's see. 13 minus 5 makes 8. 8 minus 3 makes 5. 5 minus 1 makes 4. 4 plus 1 makes 5. 5 plus 3 makes 8. I'm starting to see the mirror image right around this 2, 4 point. There's a mirror going up and a mirror going down. Okay, let's plot some of this. I'm going to start with 2, 4 because that seems like the pivotal mirror point here. So 2, 4. 1, 2, 1, 2, 3, 4. Got it. 1, 5. And 3, 5. Oh boy. 4, 0, 8. And 4, 8. 1, 2, 3, 4 to the right, 8 vertically. Okay, so it's a little bit higher in space in this one. And there's our parabola, or the graph or the image of our quadratic. So let's talk. What is a parabola? And in what I'm going to put as the definition of a parabola is the shape of the image of a quadratic function. So, shape of the image when graphing a quadratic function. Okay, they're just so popular we have a name for it. Sometimes they open up and sometimes they open down. Got it. But they all have this peak or this pivotal moment when it changes from going up to going down or from going down to going up, and that's the vertex. So this peak or this changing moment is called the vertex. It's the highest or lowest point on a parabola. Highest or lowest point on a parabola. Oh boy. Another notification. The peak, if you will. And then the axis of symmetry. So as we are graphing these, we see that they're mirror images. Goes right through this peak or this valley, the lowest point, right? So the axis of symmetry is a line across which the parabola is a mirror image. So line across which the parabola is a mirror image of itself. All right. So what I'm going to do now is I'm actually going to backtrack just a little bit. So if I go back up here, right, then I see I can build this line that goes straight through the vertex, right, which is right here. So the axis of symmetry line goes straight through the vertex and you see a mirror image. Now, let's see, does that happen on some of these other ones? Okay, So going in reverse order here. Okay, here we go. So we see here's the valley right there. There's the vertex. Here's the line of which it should be a mirror image. Man, my art is not super great here. I feel like here's the peak. And if I put this line right here, it's a mirror image across that peak. Okay, so it went up, vertex, came back down. And it's a mirror image across that center line. Here, the center line is actually the y-axis. Here's the peak. It came down, hit the peak, went back up. Yeah? Okay, so these are attributes of the parabola.
It's time for lunch, Mom.
Thank you. I'll be down in a minute. Apparently it's time for lunch in my house.
Leah took
Nope.
my job.
Nope.
Leah.
Okay, everyone. It looks like I'm going to have to change plans and stop this video and put in these remarks in my next video.